All right, so 8.2 is about circles and ellipses. Remember, 8.1 was about conic sections in general, and then specifically about parabolas. So our second type of conic sections are ellipses, and a circle is a special case of an ellipse. So often when we think of ellipses, we call them ovals, but an ellipse is like an elongated circle. And what's special about an ellipse is that there are actually two foci, and every point on an ellipse has the same distance if you add up the distance from the focus to that point and from that point to the other focus. So every point on this ellipse has the same sum of distances to the foci. Foci is the plural of focus. And the center is exactly halfway between the foci. The vertices are also an equal distance from the center. So there's a lot of symmetry going on here, okay? Now, if you want kind of a trick on how to sketch an ellipse, you can take the lengths or the denominators, and we'll be talking about standard form in a minute, okay? But if you take those denominators and you create a rectangle, an ellipse fits nicely inside of that rectangle, okay? A circle is a special case of an ellipse. It's an ellipse where both foci are the same point. So if I were to kind of squish these two foci together until they met at the center, that would be a circle, which is why a circle doesn't have a center and two foci. It just has the center, and then this distance is the radius, and it's the same for every point on the circle. Okay, so if you can recall, the equation for the unit circle we said was x squared plus y squared equals 1. And for any circle with a radius r, we said was x squared plus y squared equals r squared. And then we could translate that circle. So if I subtract a value from x or subtract a value from y, that represents a horizontal or vertical translation. Okay, so if what we can do is we can take that equation, divide everything by r squared, and we end up with this form. And this is the standard form of an ellipse. Okay, now this one, because the denominators match, is a circle. If the denominators don't match, instead of calling it r, we call them a and b, and that is the standard form of an equation for an ellipse. So let's go ahead and talk about some of the special features of an ellipse, just like we did for a parabola. Okay, so an ellipse, here's our definition. The set of all points in a plane whose distances from two fixed points, which are called the foci, have a constant sum. You can explore that more with the GeoGebra exploration that I provided on the 8.1 packet that's also linked on Blackboard. The longest distance across the ellipse, so if we look up at our picture up here, that's the distance between the two vertices, is called the major axis. And the chord perpendicular, so if we look up at our example, this is our major axis, and the one going the opposite direction, the perpendicular direction, would be called the minor axis. So let's fill in our chart. Sorry for all the moving back and forth. The standard equation, and we're going to say with a greater than b, and that way we can just always say that a is our bigger denominator. So the standard equation is x minus h squared over a squared plus the quantity of y minus k squared over b squared equals 1. This is the equation that we just saw above. And what this represents, because a is bigger, it represents our major axis in the x direction. So it's an ellipse that looks like this. Now I'm exaggerating that. Obviously, not all ellipses will be that obvious to have a major axis so much longer than the minor axis. So since our major axis goes in the direction of our x-axis, the same direction, our focal axis is also that direction. So the foci are on this line here, and that's going to have the same height as the center of our ellipse. Now the center of our ellipse, h and k, so our height is k. So that will give us the equation y equals k as our focal axis. So if our center here is hk, then our focal distance here is what we call c, focal distance of c. So to find each foci, I take hk and I'm adding and subtracting c, notice, to the x value because we're going sideways. So this is h plus or minus c, comma k. And the vertices are over here on the ends, and they are a distance of a away from our center. A being the denominator of our x, but the denominator is squared. Now again, this is changing our x direction, so we have h plus or minus a, comma k. And then we want to know what is the length of semi, meaning half of our major axis. So I'm going to draw a picture again here. Here's the center. Here's half of our major axis as a distance of a. So a is half or semi major axis. Then the semi-minor axis, if we draw on our ellipse, here's our center. Here would be half of our minor axis, that is b. B from the denominator underneath our y value. And then we have this relationship because we have C, we have A, and we have B. So if I were to draw these values, here is A, here's C, here is B, these are perpendicular, then the distance A from the center to the vertex is also the hypotenuse here of our triangle with B and C. So we say here's B, our semi-minor axis, C is our focal length, then A would be the hypotenuse. So we get A squared equals B squared plus C squared. This is different than the Pythagorean theorem. Okay, so this is all for an ellipse that goes sideways, a horizontal ellipse. And we could do the same process for a vertical ellipse. But now it's our y that will be over A because we said A is our bigger value. So we have y minus k squared over a squared plus x minus h squared over b squared equals 1. Vertical ellipse. So our focal points, align vertically. So x equals, and where is it horizontally is how much has it shifted. X equals h. From our center, which is hk, we have our focal distance of c, and it's changing our y values. So we have h, comma, k plus or minus c. And our vertices, again, our greatest distance is still called a. So now we have h, comma, k plus or minus a. And then I'll go ahead and draw a picture again here. From the center to the vertex is our major axis. So our semi-major axis is still A. From the center to the semi-minor axis is still called B. And that relationship that we had before, where this A and B and C, and so we can draw A that way, that still holds. But now B and C have kind of switched places. But the Pythagorean relation is still the same. So that's our content for ellipses. Those are our important points. So now we need H, K, and not P, but A, B, and C. H, K, A, B, and C are our important variables for ellipses. So let's take a look at some examples. Our first example And we're going to use astronomy for both this and the next section of notes. So our first example is about planetary motion. Did I skip one? Because that's example 5. Oops. Okay, sorry, I skipped a page. Example 1, we just want to find the pieces of the ellipses, and then we'll talk about how it's related to astronomy. So example 1, find the vertices, the foci and foci of the ellipse 4x squared plus 9y squared equals 36. Well, notice this is not in standard form. So how do we put it into standard form? Well, I need to divide so that this side is just 1. So we need to divide everything by 36. Now, luckily, 4 goes into 36 evenly, and 9. So we end up with x squared over 9 plus y squared over 4 equals 1. Our first step is to identify which of these denominators is bigger, 9. So we can write this as a squared equals 9, then a is 3. If 9 is our bigger, then 4 is our smaller. Smaller is b. So b squared is 4, then b is 2. Why do I use the positive values? Well, a and b represent distances, right? It's the distance of our semi-major and our semi-minor axis. So we're going to take the positive value for this when we take the square root. Okay, so since our major axis is in the direction of x, I know this is a horizontal ellipse. Okay, nothing has been added or subtracted to x or y. So just like with the parabola, I can find my center by looking at what has been added or subtracted to the x before it was squared, and the y before it was squared. So we have our center here at 0, 0. We have our semi-major axis is 3. Our semi-minor axis is 2. Okay, we want to find the vertices and the foci. I can use the information I have right now to find the vertices because a distance of 3 in either direction will give me the points. This is an x value of 3, so this is 3, 0. This is an x value of 3, but to the left, so this is negative 3, 0. So the vertices are at 3, 0 and negative 3, 0. The foci require a little bit more work because the foci need to be at a distance of c. How do I find the distance of c? Well, here's my triangle. I've got c that I don't know, b is 2, and a is 3. 3 squared equals 2 squared plus c squared. So c squared is 9 minus 4. So c is the square root of 5. So that tells me I need to take my h value of 0 plus or minus the square root of 5. So that's the square root of 5, 0, and negative square root of 5, 0. So we have A, B, C, and we had HK is 0, 0. H is 0, K is 0 from the numerators of our standard form equation. Let's try example 2. Find the equation of the ellipse with foci at 0, negative 3, and 0, 3, whose minor axis has a length of 4. Notice this is the minor axis, not the semi-minor axis. So what that tells me, if I have foci at 0, negative 3, and 0, 3, the first thing I can do is I can plot. The center is going to be halfway between those. So I have 0, negative 3, and 0, 3, and halfway between them is the center. So this is a vertical ellipse. And we know that the minor axis, the shorter axis, has a length of 4. 1, 2, 3, 4. And it has to be symmetric around the center. So here's my minor axis. That tells me I have a B length of 2. B equals 2, which was 4 divided by 2. Because if my minor axis is 4, My semi-minor axis is 4 divided by 2. Okay, but we want the equation of the ellipse. So I have B, I need A. Well, I also have C, which is a distance of 1, 2, 3. So I have C equals 3 and B equals 2, and we need to find A. Well, if I draw my triangle, A is the hypotenuse. So A squared equals 3 squared plus 2 squared. A equals the square root of 13. Okay, so we have A, B, and C. We need H and K, but I know the center here is halfway between my two foci, so the center is at 0, 0, meaning H is 0 and K is 0. So let's find our equation. We've got all of our variables. We have x minus h squared over, now my x direction is my minor axis. So that's going to be over b squared plus y minus k squared over a squared equals 1. H is 0, k is 0, b is 2, and a is the square root of 13. So we have x squared divided by 2 squared is 4, plus y squared divided by square root of 13 squared is 13, equals 1. Once you've found your variables, substituting into your formulas is pretty straightforward, but you need to know which formula to use, and you need to know which variables to look for and what they all mean. Let's look at another example. So, example 3. Find the standard form of the equation for the ellipse whose major axis has endpoints -2, 1 and 8, 1, and whose minor axis has a length of 8. So the first thing I'm going to do here is plot these points. -2, 1, 8, 1. If the endpoints of the major axis, so that's also called the vertices. Okay, and that means the center has to be halfway between them. So if I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, the center is 5 units away. 2, 3, 4, 5. Here's the center, which is at 3, 1. Okay, so the center is at 3, 1, which means H is 3 and K is 1. Minor axis has a length of 8, which means that B, my semi-minor axis, is 8 over 2, which is 4. B is 4. A, we also know because we just counted the major axis to have a length of 10, which means A equals 5. So what are we missing? We're missing C. Now, we do need C in order to find the foci, and we do need C in order to have the complete information for this ellipse. However, all we're looking for is the standard form of the equation, and we don't need C for that. So at this point, you can find C, but you don't have to. So we're going to go ahead and find our equation. X minus h squared over, our major axis is in the x direction, so that's A, plus y minus k squared over b squared equals 1. H is 3. X minus 3 squared over A is 5. 25 plus y minus k is 1 over b squared equals 1. So again, the hardest part is knowing what to find and how to find it, and then substituting it in. You have the formulas, so it's pretty straightforward. All right, our next example, we want to find the center, the vertices, and the foci of the ellipse with the equation. So we're doing those last couple of examples, but backwards. Okay, so the first question we have to ask, Which one is A? Which one is B? The larger one is A. So our larger denominator, 49. A squared is 49. So A is 7. B squared is 9. So B equals 3. H and K are the number that was added or subtracted to X and Y. So here I'm looking at X minus H. So X minus -2. So H is -2. X minus 5. So K is 5. Okay, so we have H, K, A, and B. We still need C. H is -2. K is 5. A is 7. B is 3. C equals what? Well, let's sketch this, okay? We have our major axis is in the Y direction, okay? Here's our center, focus, vertex. There's C, that's A, that's B, so this would be A. So then C squared equals A squared minus B squared. My bigger one minus my smaller one is my unknown one squared. So C squared equals, A squared is 49, minus B squared is 9. So then C equals, well, let's simplify, the square root of 40, which is 4 times 10. 4 is a perfect square. So that's 2 root 10. Okay, but that's not what we're looking for. We need A, B, C, H, and K. But what we want to find is the center, vertices, and foci. So the center, which is HK, is -2, 5. Vertices, the vertices is all the way distance to A, so that's changing my Y value, H, K plus or minus A, which is -2, 5 plus or minus 7. So that's 5 plus 7 is 12. 5 minus 7 is -2. And then we have the foci, which are the distance C, H, K plus or minus C, equals -2, K plus or minus C, 2 root 10. That's not going to simplify, so we can leave it that way. So there are all of our points. Okay, so we finally made it to the next page, which is the much anticipated example that I started to show earlier, and that is astronomy. Okay, so Kepler's first law of planetary motion was published in 1609, and it states the path of a planet's orbit is an ellipse, with the sun at one foci, so at one of the focuses. Asteroids, comets, and other bodies that orbit the sun follow elliptical paths. The closest point to the sun in such an orbit is called the perihelion, and the farthest point is called the aphelion. Okay, so if here's the sun, then the distance to the closer vertex is the perihelion, distance to the farther vertex is the aphelion. Okay, the shape of the ellipse, so how far it's stretched, is called its eccentricity. Okay, so E is C divided by A. The distance to the focus divided by the distance to the vertex. So it's saying how far off is it from a circle. Now this E for eccentricity is not the natural base E. So this is not the E that's 2.71. So let's take a look at example 5. Earth's orbit has a semi-major axis of A and an eccentricity of E. Calculate and interpret B and C. Okay, round to 3 decimal places. Well, we know it's semi-major axis, so we can use the diagram above. If this is the path of Earth's orbit, its semi-major axis is the distance not to the vertex, but the perpendicular distance. So here is, let me do it horizontally. And I'm I'm accentuating this so that we can see it clearly. Here's the center. That would be the semi-minor axis, and this would be the semi-major axis. So we're talking about the distance from the center to a vertex is 149.598 gigameters. Okay, so that actually tells us the distance from the center to our points of aphelion and perihelion, our vertices. So what we want to do, we have our eccentricity, we have our semi-major axis, which is A. If we have E and A, then we can find C. So we have E equals C over A. 0.0167 equals C divided by 149.598. Multiply both sides, we get that C equals approximately 2.49. Oops, started drawing sideways. 2.4982866. Okay, well, if I have A, B, and C, I have A and C, so we need B. Well, B squared, remember B, A, C, B. So B squared equals A squared minus C squared. And we're going to put these in the calculator. 149.598 squared minus 2.498 squared. Into the calculator it goes with a square root. B is approximately 149.577. Okay, so we've got A, B, and C. But what are B and C? Okay, well, B is that distance from the center on the minor axis, and C is the distance from the center to a focus. Remember, one of our foci is the sun. Okay, so C is the distance from center to sun, and B is the distance from center on the minor axis. Since A and B, so A is 149.598, B is 149.577, those are really close in size. So Earth's orbit is almost circular. You could also conclude the sun is near the center. Oops. Okay, so there's a lot of things you can conclude and you can interpret, but the important thing to recognize is what those values of B and C mean. All right, let's look at example 6. This is the last part. Okay, so in example 6, we're looking at another application of ellipses. However, this is actually an ellipsoid, meaning three-dimensional ellipse. So let's look at this property of an ellipse. Now remember, for a parabola, we could think of it like a speaker or a flashlight. Well, for an ellipse, we have to think of it more like an enclosed space. So because of their shape, ellipses are used to make reflectors of sound, light, and other waves. If we rotate an ellipse in three-dimensional space about its focal axis, the ellipse sweeps out an ellipsoid of revolution. So we just call a three-dimensional ellipse is called an ellipsoid. If we place a signal source at one focus of an ellipsoid, the signal reflects off the surface to the other focus. So this is commonly seen in architecture, where you'll have an ellipse-shaped room, And at one point you could whisper and you could hear it very clearly in another point. There are a lot of famous buildings that this happens in, including, I believe, the San Diego courthouse, but I'm not 100% sure about that. So, example 6. The ellipse used to generate the ellipsoid of the lithotripter is a machine used to treat kidney stones, has a major axis of 12 feet. Major axis is the long one, is 12 feet. And a minor axis, that's the shorter one, of 5 feet. How far from the center are the foci? Well, so this question is actually asking for the value of C, the distance from the center to the focus. Okay, what does the 5 represent? It's the it's the minor axis. Well, B is the minor axis over 2, is the semi-minor axis. So B is 2.5, and A comes from half of our major axis. So A is 12 over 2, or 6. Okay, and if this is my center, hard to see on this diagram, this is my center, C is what we're looking for, B is 2.5, and A is 6. So we have C squared equals 6 squared minus 2.5 squared. 36 minus 6.25. C squared is 29.75. So then C is the square root of 29.75, which is approximately 5.45 feet. So C equals 5.45 feet from the center. Why is this important to be able to calculate? Well, if I'm let's say a medical assistant and I'm situating the patient in the room for the lithotripter, I need to know where should I line up the patient so that their kidney is located at the focus of the room, so that it's essentially ultrasound that breaks up kidney stones will work on just the kidney stones, and it can be the most effective treatment possible. Okay, what I'd like you to do is do a summary, 1 to 2 sentences, and I'm going to have you submit that through Edpuzzle. There's a feature on Edpuzzle where I'm going to post an answer or a question. You'll see it in a second. You can type in your response, and it just kind of gives me an idea of where we're at. If you have questions on this, we can address them next class. I have a Blackboard discussion available for you where you can post your questions and you can go on there and answer each other's questions, and I'll be looking through as well. But I'm going to pick questions to answer from there next class, our virtual class, if they are posted before midnight, before our class. So if you post a question at 7 a.m., I'm not going to have a chance to prepare that for class. So the question has to be posted by midnight, the night before our class, if you want me to address it in class. And then if we have extra time in class, I'll obviously address more questions if they come up.